Hello and welcome to the course Design Borefields with Confidence. This is the introduction video of already the fourth part of this course. But before we jump into what we will be covering in this part, let us revisit or recap what we've been doing over the last couple of chapters. Now, the previous part was all about how you can make better borefield design using newer, more state-of-the-art assumptions and models. And we started off that part by a discussion again about monthly versus hourly temperature profiles. And we said that the main advantage of using hourly temperature profiles is that we can see when we cross a certain temperature limit, how important that is, or what the effect of that is on our total system. We can see whether we cross a temperature limit for 1 hour or for a whole week, let's say. And when we use monthly simulations, this is a kind of nuance that gets lost. And secondly, we also said that when we're working with hourly temperature profiles, we do not need to estimate this vague parameter of the peak duration. So in general, when we have hourly data available, it's better to use it. It can give you more insight in how your geothermal system behaves. Next, we talked about more state-of-the-art methods. For example, the first thing we discussed is the use of variable fluid properties. Now, historically, typically when you design a geothermal borefield, you select your fluid, and the viscosity, density, and so forth were calculated once. And this means you have one Reynolds number, one borehole resistance throughout the whole simulation period. Now, as we discussed, this is a very radical assumption and not very accurate. Because when you're using your borefields, in particular for both heating and cooling, your temperatures can easily fluctuate with 20 degrees Celsius between the extraction and the injection. So of course your Reynolds number will also vary because your viscosity is not the same at all these temperatures. And we discussed that when we update the Reynolds number and the borehole resistance at every hour of the simulation period, we can get way better insights in how our temperature profile really looks like, take into account these variable fluid properties. And we risk oversizing significantly, especially for borefields that have quite a lot of cooling demand. Now, besides working with variable fluid properties, we also discussed working with variable flow rates. Because that's another traditional assumption that our flow rate during heating, cooling, and the whole year is basically constant. Now, of course, that's also not what happens in reality, since nowadays most circulation pumps are actually frequency controlled. And most pumps now work that there is a certain constant temperature difference across the heat pump. So it's not our flow rate that's constant and the temperature difference that varies, it's the other way around. Our temperature difference across the heat pump is constant and hence our flow rate will vary. And we saw that when working with these variable flow rates, we can get again way better insights, especially in how the temperature profile looks like when we're not working at peak powers, but also we can risk over and undersizing, in particular when the heating and cooling peaks are not the same. Because if they're not the same, the flow rate is not the same, and it can be that we overestimate the Reynolds number and the flow regime in one case or the other. So also there, in order to make sure that you have an accurate, not over or undersized design, it's better to use variable flow rates. And the third major assumption we want to get rid of is that of the use of variable efficiency. Now, historically, we all said, well, let's use a constant SCOP to convert the building load to a ground load. And there are a couple of problems with that, namely that we convert the energy and the peak demand with the same factor. Although, as we discussed in the first part, there is a difference between the seasonal coefficient of performance and the immediate, the actual coefficient of performance. And also when the efficiency is an input, it does not matter what your design is, whether you're drilling deeper or less boreholes or if you change the configuration. Now in reality, of course, this has an effect. And we saw that when we actually work with modulating heat pumps directly in GHG2, we can get way better efficiencies than the ones on paper. Because of course, on average, our fluid temperatures are also higher than during these standard B0W35 or B0W55 measurement points. And it will give you better insights in what effects on the changes of your design, how that reflects on the efficiency of your system. So that was everything we covered in the last part. Now in part 4, the focus will not be on the thermal side of things, but on the hydraulics, which is often also overlooked when designing bore fields. Now in this part we will start with a discussion on what exactly is the pressure drop. What is the difference between local or major pressure drops, and why do we care, and why is it important that we take a look at the hydraulic side of things? Why do we care about this pressure drop when working with geothermal bore fields? Once we understand this concept, let's deepen these insights in the second chapter, where we will be talking about pressure drop, but again with these newer assumptions of variable fluid properties and variable flow rate. Because this again can give us quite a lot of insight in how our system behaves, not only thermally as discussed last part, but now also hydraulically. And we will also introduce the concepts of the pump power and the pump energy. And in the third chapter, we will make everything more practical and talk about the actual hydraulic design, taking into account the horizontal connections, the series entanglement connections, whether you use single or double boreholes and so forth. And also how you can do that in GHG yourself, so it will be a little bit more hands-on this last chapter. So I hope you're buckled up. Let's jump into it with the first chapter.